Okay, well, that's a great jumping off point to exoplanets, I guess.
Okay, yes.
Which I'm told is your new obsession of sorts.
Well, it's for a while. When I started, even as an undergraduate student, I was interested in stars and the vibrations of stars to probe their structure and their life histories. And that remains a passion for me. But the techniques that we would use to try to probe inside the hidden interiors of stars are also the same kinds of techniques and instruments that one would use to detect a planet, an unseen planet around another star. And when I arrived here at UBC, one of the reasons I came here was because one of the pioneers of exoplanetary science was here, Gordon Walker, who together with a young astronomer at the University of Victoria, starting in the late 70s, and that young astronomer was Bruce Campbell, not the Bruce Campbell of Evil Dead and Army of Darkness fame, but they had come up with an idea of how to actually start a search for exoplanets. Exoplanets, by the way, is the term for any planet beyond our solar system, orbiting any star other than the sun. The problem was at the time, scientists had realized that you could detect a planet by its gravitational influence on the star. You couldn't see the planet, too faint to be seen. You know, if alien astronomers are trying to take a picture of the Earth beside the sun is 1 billion times brighter than the Earth, and the Earth is going to be lost in its glare unless you use very specialized techniques, which we don't have yet, but we're working towards. And so when you think of an orbit, say the Earth around the sun, you tend to think of the sun fixed at the center. It's at the center of the solar system. But nothing is really nailed down in space. Nothing is tacked down. And so the fact that the Earth is orbiting around the sun is due to gravity. But gravity is a two-way street. Gravity is a mutual attraction. So if the sun went up to the Earth in a bar, it could say, hey, we're attracted to each other and the feeling is mutual, but don't worry, it's purely physical. And that would be a very accurate statement of what exists in terms of the sun and the Earth and any star and any planet. And so the gravity of the sun, Earth attraction, is able to keep the Earth in this wide orbit. But it's a two-way street. The same force that the Earth is feeling from the sun is feeling from the Earth. It's just that the sun is 300,000 times more massive than the Earth, and so F equals ma, force equals mass times acceleration. The Earth is accelerated a lot, and so it's in that big, wide orbit, but the sun is accelerated but a little. And so the sun is also forced to orbit kind of a balance point. I think of it as dance. Basically, it's like you have two swing dancers swinging around, their arms or their elbows are locked together, and they're swinging each other in a whirling dervish as fast as they can. And if they're equal weight, equal mass partners, then they will swing about a point which is directly between them. But now let's say you have a father swinging his baby daughter around, and now the daughter goes around in this kind of wide arc, and the father wobbles around a little bit. And that's the situation that you have. The father is the star, the daughter, the baby daughter, is the planet. And so Gordon Walker and Bruce Campbell realized that you needed a very high precision in measuring the speeds of stars, that you had to build a stellar speedometer, kind of like a radar gun for stars, except that you wouldn't need to bounce a signal off of them, that you could use the light coming from the stars and measure the Doppler shifts as the star is wobbling due to an unseen planet. The problem is that the level of wobble, the speeds that you'd need to measure with this radar gun, with this speedometer, would be measured in like tens of meters per second. And the precision at the time, astronomical precision, was about 1 kilometer per second, 1,000 meters per second. And they came up with a way to improve that precision, by more than an order of magnitude, and finally bring planets within the realm of detectability. And they searched, I think it was about 16 sun-like stars for many years, and they actually found a planet. But they were, cautious scientists and polite Canadians, and so they didn't kind of trumpet, hey, we found a planet. They said, well, we have found a signal that looks like a planet, but it doesn't look like any planet that we have in our own solar system. So we're maybe a little suspicious. We want to, make sure that we check everything, that we're not being fooled by something that the star is doing that might mimic the signal of a planet. And we still have to deal with those. We call them false positives. But as it turns out, they had found a planet in 1987 around the star Gamma Cephei, in the constellation Cepheus. So now the star would be, and the star was already part of a binary system, a widespread binary system. So it was Gamma Cephei capital A, and now the planet around it would be Gamma Cephei capital A lowercase b. But 8 years later, when Michel Mayor and Didier Queloz, the Observatoire de Genève, the Geneva Observatory, found this kind of wobble signal in the star 51 Pegasi, they didn't hesitate to call it a planet. They just said, hey, we found a planet, even though the signal was unlike any planet that we'd ever thought about that we have in our solar system, hot Jupiter. Gordon was one of the referees of the Nature paper. I had a chance to look at the manuscript of the Nature paper, and to be honest, I didn't believe it was a planet. I thought it was something else that the star was doing, but the signal was so convincing that you just couldn't you couldn't stop having those data out there and people following up on them. And then eventually there were other examples, and we found out that we used to think our solar system was typical, and that might not be the case. We might be one of the oddballs in some ways. So I had the opportunity to be at the ground floor of exoplanetary discovery, coming here to UBC as a young astronomer, and so it was a natural transition to include that. And then when Canada's first space telescope was proposed and funded and designed, and we had started cutting metal, building it, it was all for stellar seismology. And it was only after we had started to build it that I realized that even I had underestimated what you could do with the right kind of instrument, even on a small telescope, in the right kind of orbit in space, and started to do some things to demonstrate that it could do exoplanetary science that nobody else could do. And I recruited Sarah Seeger, who's a Canadian, who's now a professor at MIT and one of the leading stars of exoplanetary research, and a student who had just finished first year, who's now a professor at the University of Toronto, who did his PhD in string theory at Stanford. And we did Monte Carlo simulations of photon scattering in simulated atmospheres of exoplanets, and then ran that through the kind of the MOST simulation to say, could MOST actually measure the reflected light from a planet around the other star? And the answer was yes. And so we added exoplanets to the mission. And I was able to go to the officials at the Canadian Space Agency in Ottawa and say, we're going to add a new component to the science mission of Canada's first space telescope. And not just something which is exciting to scientists, but is exciting to the general public. And we're not going to have to change the design of the satellite. We're not going to have to change the way we operate the satellite. And more importantly, we're not going to have to add one loonie to the budget, which is not something you get to say very often. So I took great relish in being able to deliver that message. And for much of the operational lifetime of the MOST mission, I would say that exoplanetary science is now a third to a half of the science that we do. And one of the first big breakthroughs we did was to actually measure the albedo, which is the technical term for the reflectivity of a planet, of a hot Jupiter, HD 209458b. Don't you love the telephone book numbers that we give to these? And it was a surprise because this is hot Jupiter. It's close to its star. It's very hot, but it's a gas giant. And in our own solar system, the poster child or poster adult for gas giants is Jupiter. And its albedo, its reflectivity, is about 50%. Half of the light that arrives in its upper clouds and atmosphere from the sun is reflected. And that's what we were expecting. But it turns out that the reflectivity of this planet could be as low as 4%. That's less reflective than charcoal. And that was a real surprise. But it was a kind of a blessing in disguise, because combined with observations in another part of the electromagnetic spectrum, infrared data collected by NASA's Spitzer Space Telescope, we could combine those two things, the optical observations from MOST and the Spitzer infrared observations, to paint the theoreticians into a corner in terms of specifying the temperature and even the composition of this atmosphere, and even if there were clouds and what those clouds were made of. And it's incredible how much you can squeeze out of such a small number of photons of light in what is, in some sense, a deceptively simple type of measurement.
Okay, so hold on. So you've got a planet that's really close to the star, but it's essentially like a black body. Like it's if this planet was out in Jupiter's orbit, would it be just a void in space?
Notice how I worded it. I said that it was as unreflective as charcoal. I didn't say dark, because this planet is orbiting 20 times closer to its sun than we are to ours. And so the light that it receives from its sun, the flux that's arriving in the upper atmosphere of this planet, is 400 times brighter than what we see on a clear, sunny day. And so even though the planet reflects only, say, 4% of the light it receives, it's receiving 400% of the light that we receive. And so it would still be a relatively bright looking planet.
Right.
It's just not as bright as it would be if it were more like Jupiter. So I'm very careful in the wording, but sometimes I cheat and just say that this planet is as dark as charcoal, which is an easier thing to say, but technically would not be true.
But what does that then? Like, what's the atmosphere made of?
Well, so in this case, going back to those kind of Monte Carlo simulations of photon scattering, just to say that it really is rocket scientist, I have to use the jargon every once in a while. In this case, it seems to be a very cloudless atmosphere. And so the photons from the star can penetrate very, very deeply before they start to be absorbed and then re-emitted and scattered. And then they have kind of a hard time to work their way back out. And so basically, one of the interpretations is that it's a clear, cloudless atmosphere in which the light penetrates deeply, and then it starts to encounter different conditions under those pressures where it's very different than anything we would have in the Earth's atmosphere. The other interpretation is that it does have cloud condensates and aerosols and dust grains in it that happen to be non-reflective or that scatter the light in many other directions. And so we can talk about reflection like from a mirror or a surface, but we can also talk about scattering, in which light comes in and then it comes out again, but it comes out at some other odd angle and it doesn't come back. You're looking at the star and the planet from this perspective in Earth, and light which would be coming from this direction would not necessarily be reflected back to our telescopes. So there are a number of possible interpretations, but the fact that the albedo, the reflectivity, is so low really does limit the options that nature cooked up this planet, and what we're doing now. I was talking about the recipe of the universe before being very simple. We used to think about the recipe of a solar system. Our own solar system was the only example, and we came up with a model, the nebular hypothesis, to explain the dynamical and compositional properties of the planets in our solar system and the sun. And we thought, okay, that's probably that's the recipe for every other solar system, until we started to find solar systems and found that the universe is working from a much bigger cookbook with many more recipes, with some different ingredients, but also many more steps. And so we realize now that our recipe for a solar system is kind of like the recipe for scrambled eggs with salt and pepper. But the universe has managed, nature is cooking up eggs Benedict, with pulled pork, and going off the breakfast menu to, beef stroganoff and lobster Newburg and pizza pops and so on. And so we are finding that although our picture of how our solar system formed is generally still correct, we think, but there are other ingredients, and there are other steps in the recipe that we weren't aware of, and discovery of these other planetary systems is making us re-examine our own, and we're realizing that some of what we would have thought were really weird, exotic things happening elsewhere might have actually happened here too, and that we are one of the outcomes of a lot of these things happening, but we just happen to be an outcome that we're so familiar with that we just kind of think of it as standard, normal, boring. But if they're alien astronomers on another one of these planetary systems, which has very different dynamical and compositional properties than our own, they might think of us as exotic. And that's what I'm saying is that we are on the verge now of having a proper census of planets in at least our neighborhood of our galactic city in the Milky Way, to be able to say, how typical are we? How common are Earth-sized planets in the habitable zone, in the Goldilocks zone, where if you're too close, it's too hot. If you're too far away, the planetary bowl of porridge is too cold, and if you're in the zone, it's just right for liquid water oceans, maybe life. And that's what we're working on right now. The Kepler team is that will be the final deliverable of the original Kepler mission, is what we call Eta Earth, the Greek letter Eta, sub-Earth. What is what would be the fraction of planets, of stars that have Earth-like planets around them? My student Michelle Kunamoto, who has only just got her Bachelor of Science degree last year and had discovered 4 new planets in the Kepler database before she'd graduated, her master's thesis with me is to basically do an independent estimate of Eta Earth through her search protocols and so on. And so it's a really exciting time. I was talking in my class, Astronomy 333, Exoplanets and Astrobiology, and you made a cameo appearance in the last lecture just a few hours ago. I'm telling them about the Drake equation, which is kind of one way of trying to give a quantitative estimate of the number of intelligent, technologically communicative civilizations in our galaxy. And there's a lot of different numbers, very few of which are very well known. But one of the numbers in there is the fraction of stars that would have planets, and then the fraction of those planets that could support life. And those numbers we didn't really know anything about because we had only one example, our solar system, and one example of life, here on Earth, unless you think that like Star Wars is a documentary movie. And now we are actually, putting real hard numbers into those variables in the Drake equation. And so it's a really exciting time compared to, even a few years ago. There are things that I would talk about and introduce to my students in class. We didn't even have the language for it 5 years ago. And that's why I can never get bored with the research I'm doing or with teaching students or sharing with the public that research, because it's just never the same.